Okay, so I apologize for taking extra time grading the exams. I got distracted by my ex, being my ex, and sharing a kid with him. Um, but I just literally uploaded this writing assignment 5 minutes ago. But I wanted to discuss sometimes students have problems with the description here, with like physically seeing what this means. So you're constructing a cardboard box with the dimensions 2 meters by 4 meters. This should say from the dimensions 2 meters by 4 meters. You then cut equal size squares from each corner so you may fold the edges. What are the dimensions of the box with the largest volume? So you're starting with a big piece of cardboard that measures 2 meters by 4 meters. So imagine our piece of paper here is the cardboard. We're going to cut squares out of each side. So I put some Post-its to kind of label the squares we're cutting out. They're all the same size square. So we can call the edges of these squares X. Then once those are removed, then we're going to have 4 like rectangles on all attached to a central rectangle, like a net kind of diagram. And then we're going to fold it up. And I was lazy. I didn't want to actually cut stuff out. So I just used some really quick folding. But now we have a box. It's missing a top, but this box has a volume. And depending on how large the squares are that I cut out, the volume of the box changes. So I can have like a really wide box because I cut out like really tiny corners, so it looks more like a cookie sheet. Or I can have something that will be like really tall and narrow, just depending on how large the squares are that I cut out. So we're going to work today on how to use calculus to figure out what the optimum square length of X is to maximize this volume. Now we're going to do it on different problems, but this is the setup for the writing assignment. So I find like seeing a visual model helps, and doing this yourself, like having a piece of paper where you can write all the lengths on it and then write the X's that you're cutting out on it. And then when you fold it up, you can kind of see, oh, I wrote an X there and now that X is here. So it can help you kind of see where the dimensions end up. All right, so let me flip the share back to OneNote now. So, Christy made some really interesting optimization problems. They have a fun sense of humor. So, you've got a bunch of piggies and you want to build them a rectangular pen, but you can only afford 780 feet of fencing. To get the most out of the material you have, you decide to use a river as one side of your pen. What dimensions should you build the pen to give your piggies the most space possible given your limited supplies? So we got some fun pictures on the first slide, but then we scroll down and we've got a repeat of the question with a blank spot. So when you're working an optimization problem, the first thing to do is to make sense of the situation being described. There's almost always either a graph to be sketched or some sort of drawing to be constructed that's going to have the information we're being given. Now, it doesn't feel like we have a lot of information here. We have one number and a shape, but this is enough to actually answer this question. All right, so we're going to start with our river. And then I've got a rectangular pen there. And I know that my fencing is 780 feet. So when we have a diagram, one of the things we get to do is we get to label this diagram with whatever variables we want. So when we're talking about a rectangle, what kind of dimensions, what kind of words do we usually use to talk about the sides of a rectangle? Yeah, usually length and width. You could say even base and height, although we usually use that for triangles, but some people use that for rectangles too. You could even just be like, I don't want to think about it. X and Y is perfectly fine. So I'm going to go with length and width. My L's are kind of weird though, so I use capital L's. Otherwise they look like ones. So we'll call the length here on the bottom. We'll call this the width here on the side. So my fencing diagram that I drew, I've got a width and a length, and then I've got one more width, right? Because a rectangle, the opposite sides are equal lengths. Now, if you did the L's on the side and the W on the bottom, that's fine. It's going to flip the dimensions you get, but you're going to end up with the same answer we get. It's just your L would be our W and the other way around, but it totally will work. So I've got two widths and a length, and those three lengths have to add up to 780. So that's one equation I have. Two W's plus an L equals 780. Now, the thing that they asked us to maximize was the space possible. So when they say the most space, like what do we call the space inside the rectangle? Area. So we want to maximize area. That's what most space is a keyword for. So we need a formula for area. So what do we know the area normally is? Length times width. Now, here's the catch with a maximization or minimization problem, an optimization problem. We want a formula only in terms of one variable. Now, it doesn't matter which variable, either direction will work. Usually one variable is easier to get it in terms of than the other, but technically they'll both work. It's just a matter of one way will have a fraction and the other way may not. Sometimes they both suck. So what we're going to do is we're going to use any other formula we have, and we're going to look at making a substitution. So I have 2W plus L equals 780. I can get L by itself without having to do any division. So that is what I'm going to do. I'm going to minus 2W from both sides of this equation. So I now know that the length is 780 minus 2 widths. Now this is a substitution I can make for L. L is the same as this expression. So I'm going to substitute it in place of L. Now remember, anytime we make a substitution, careful math, wrap it in the condoms of mathematics, use the parentheses. Some of you guys were not remembering the parentheses on the test. So now my area equals 780 minus 2W times W. So I could take the derivative now, but that would cause a product rule, and I'm lazy, so I'm going to multiply the W through first. So this formula, A equals 780W minus 2W squared. If we graphed this, this is an upside down parabola. So this parabola has a maximum point at the vertex. And in previous classes, we had a formula for the vertex of a parabola. But now we know calculus. So when we're looking at where the maximum of a graph is, what's special about that top point on a graph? What's zero? Well, so the graph can be shifted like up and down. So the y value is going to change just depending on what the numbers in the graph are. But the derivative is zero. So whenever we're doing an optimization problem, once we come up with a formula all in terms of one variable, we're looking for a max or a min. That's just a critical value of the graph. So I have a formula. I'm going to take the derivative and set it equal to zero. So A prime, now we're doing the derivative of 780W. So that'll just be 780 minus 2 times the derivative of W squared will be 2W to the first. And now we're going to put 0 in place of A prime. So this is 780 minus 4 W's. And now I'm just solving, so I'll add the 4 W's to the other side. And then we divide by 4. We get 195 for the width. Now they asked what dimension, so I need both answers. So I need the 195, but then I also need to take this number and come back to my formula for length and substitute it in there. So length equals 780 minus 2 times 195. That'd be 780 minus 390, which is 390. So our maximum area pen has a length that is twice as long as the width. So it's like 2 squares smushed together or perfectly adjoined. And when you do these problems, you're going to see like a square is very often a maximum area thing. Here we're getting 2 squares because one of the sides we didn't have to build a fence on. But if we were just building a rectangular pen with all 4 sides, we would have ended up with a single square. All right, so we drew a picture. We labeled the dimensions in the picture. We came up with a formula from the information they gave us about the fencing. And we came up with a formula for what we were being asked to maximize. We wrote the maximization formula in terms of one variable, took the derivative, set it equal to 0, solved that, plugged that number into other formulas we had so we could get all the dimensions to answer the question. Now, sometimes they'll have like the question they ask may require you to do like one more step after you get the answer, just depending on how the question is phrased. So be on the lookout for that. Usually when they do that though, they'll have like a space for like, what was your solution? And then what's a follow-up thing? Like here, they could ask, what is that maximum area? And we could just do 195 times 390. And if they wanted, they could say like each pig needs 50 square feet of space. So how many pigs could you have? So we could take that area divided by 50 square feet and then say, okay, here's how many pigs you can have. So we defined all the variables, drew a picture. Make note of any constraints or restrictions on the variables. So the constraint was our length of fencing. Technically, there was another restraint. We don't talk about negative lengths of fencing, and a fencing length of 0, like one of the dimensions being 0, would be rather silly. But those also do provide constraints, and sometimes those like end note constraints end up being the answer because the rest of the problem is weird. So identify the quantity you're optimizing, write an equation relating the quantity with the other variables, and then use the constraints so the equation is only one variable. And then find the derivative, set it equal to 0, and get the critical points. They really like SpongeBob. But I have to admit, like, I had never seen this picture of Shrek Crocs before, and those are pretty awesome. I don't wear Crocs, but those are awesome. So imagine you're on Grindset trying to get that bag. So you started an Instagram shop selling vintage Crocs. You have over 30 followers and things are going great. You just aren't sure how much you should be charging. When you first got started, you sold them for 50 a pair and you were selling out every month. Fixing to stay on that grind, you slowly raised the prices until they reached 200 and people stopped buying entirely. Based on your experience, you found that for prices P between 50 and 200, the number N of sales you make a month is given by this formula. N of P equals 1,000 minus 5P. How much should you be charging for each pair of vintage Crocs to get rich quickest? So we have a giant paragraph of text because they like telling a story. That's all right. So our question at the end was how to get rich quickest. So how to get rich. This is about making most money. Go for it. So they didn't tell us anything about how much they cost to make. So we're just going based off of the price and how much money we'd make from that. So I guess yeah. Now, a different setup of the problem, they can also talk about costs, and then you have to relate that information in there. But when we ask those questions, like we usually reserve that more intricate setup for the business calculus class. So we just consider it from a more vague, straightforward sense here. Not that it's incredibly complex. You just you subtract your costs off of your price. That's your net profit. And then you'd multiply by how many items you're selling. So our get rich quickest, we're trying to maximize money. So I've got two variables set up by the problem. I've got the price of each pair of Crocs, and I've got the number of sales I can sell for the Crocs. So P and N. So on these problems, especially when the question sets up variables for me, I like to write down the variables and write down what they represent. So P is the price per Crocs. And then N is the number of sales, so the number of Crocs sold. So how do I figure out my profit? Or my money coming in? N times P. And this is what I want to maximize, but I've got two variables in there. So I go back to the other formula they gave me. So they wrote it as N of P equals 1000 minus 5P. So N of P is function notation, but we can just strip this away and just call it N. So N equals 1000 minus 5P. So I'm going to make that substitution in place of N. Now I have a formula only in terms of one variable. Now I can use my calculus. So I'm going to clean up the formula first, though. Just multiply that P through. So 1000P minus 5P squared. Yet another upside down parabola. So we take our derivative, M prime equals 1000 minus 5 times 2P. And we set it equal to 0. So I'll add the 10P. Equals 1000, and then I divide by 10. So I get P equals 100. Now, when I finish, I like to go back and check this back with the units, what I described the variables as. So my 100 here, is that how many Crocs I'm selling, or is that the price per Croc? That's the price per Croc, because it was P and we said P was the price. So P equals $100 per Croc. Now we could plug into the formula to see how many Crocs we're selling. 5 times 100 is 500. 1000 minus 500 is 500. So that's a lot of Crocs you got to get your hands on to sell. But this is a very simplistic version of one way to consider how to maximize profits with zero regard for the ethics of doing so, but selling a non-essential item, well, you sell it for what people will pay you for it. So questions on how this one went? Now, this was strictly from a revenue perspective, like the money we got, that was just our incoming revenue. If we knew costs, like rent they were paying on the facility, their storefront, and and then how much money it costs per pair of Croc, we could actually incorporate that in here and have a profit function and then take the derivative of the profit function. And then there's even like fancier math you can do that's called marginal profit, that is looking at like how much money you make per Croc as you change the number of Crocs you make. But that's a fancy thing that we leave for business calculus. Not that y'all can't do it, we just focus on more peculiar questions. Oh, yay, we are doing the box question. So imagine it is winter break and you just finished your last final exam. You are so excited to finish packing and go home for the holidays when you realize you're out of cardboard boxes. Thinking fast, you grab an old 24 by 36-inch poster board from a final project you threw together last minute and got an A on, obviously. And you cut a square from each corner to fold it up into a makeshift box. You really want to go home, so you need to make sure all the rest of your stuff fits. How large should you cut the corners from the box to have the most room inside for your things? So here's just the basics of the problem without the story. A 24 by 36-inch poster board. So there's our poster board slash piece of paper. And there's my Post-its going down. And there's my 24 and my 36. Now, for each of the corners that we're cutting out, they're squares. So I know each side of the square, I'm just going to call that X just to give it a label. And now, like, remember, I drew in the folds. Now I made some funky diagonal folds. We don't need to copy those parts down. But from each corner of the square, like that I cut out, I'm connecting it to the other corners of the squares. So I'm going to sketch in this bottom rectangle that got formed after I remove those pieces. So what can I say about the dimensions of that rectangle? Yep. Now, if seeing that is like my brain just exploded, what did you do? So one of the things I'll do on a problem like this, if doing it with variables is kind of confusing me, I'll pick a number for X. So if X was a Post-it is actually 3 inches by 3 inches. So if I cut a Post-it out of each corner, I'd have the 36, and then I subtracted 3, and I subtracted another 3. So I'd take 3 off 2 times. So it'd be 30 inches, but I got 30 by subtracting 2 times 3. And then the 24 minus 3 would get us down to 18, because that's 24 minus 2 times 3. But 3 was my X number, so then I just write that calculation I did with X's instead. So kind of a weird way to think about it, but that can give you a way to like sink your teeth into the problem, what you're supposed to do with it. Now, I will say part of the reason I put this on the writing assignment, one, I forgot we did the example in class, but two, the question itself is a little too long for the test, but it's a really good maximization problem. Like this is a thing you literally could do, and figuring out how big do you want to cut out to make a big enough box, like has meaning. All right, so I've got the dimensions of the rectangle on the bottom. So when I fold up the box here, I'm going to kind of make this more 3D looking. So this is my 36 minus 2x. This is my 24 minus 2x. And then how tall is the box going to be? Yep. That's the side length of my Post-its. So what is the volume of that box? Or what's the volume of any box? What's our formula for volume for boxes? Yep. Length times width times height. So take a side times another side times the third dimension. So we get a formula that is actually already in terms of one variable. But our next step is take the derivative of that. So numbers are a little annoying here, but we're going to FOIL this whole thing out, and then we'll multiply everything by x. We could do a like nested product rule. And if you want to do it that way just to be fancy, that's fine. I just usually multiply it out because that's usually less problematic. 36 times 24 is apparently 864. Minus 36 times 2 is 72x. Minus 48x. Plus 4x squared. And then everybody's going to get an x. Now, this is still just our volume. We have not done any calculus. We're still just doing algebra cleanup. So I will have 864x minus 120x squared plus 4x cubed. And if you want to write that like biggest power to smallest power, that's fine. I'm just going to leave it like that, and then we'll start doing the calculus. So the derivative of 864x will just be 864 minus 120 times derivative of x squared is 2x plus 4 times derivative of x to the third is 3x squared. And we're going to set this equal to 0, and now I have a quadratic. So now I'm going to go to the effort to write it in order. So that's 12x squared minus 240x plus 864. Now I can take those three numbers, shove them into the quadratic formula and work it out. But the solution to this quadratic is the same as the solution to a reduced quadratic. So everything here is actually a multiple of 12. We got 864 by doing 36 times 24. There's like extra 12s in there. So I'm going to factor the 12 out just to make the resulting thing not so ugly looking. So it's now x squared minus 20x. And then what do we get? 72? Cool. Plus 72. That's 8 times 9, 12 times 6. I don't believe that factors nicely. All right, so we're going to use the quadratic formula with 1, negative 20, and 72. All right, so x equals negative 20 plus or minus the square root of negative 20 squared minus 4. Ugh, bad handwriting. 4 times 1 times 72 all over 2a. So we have 20 plus or minus, let's see what we get. 20 times 20 minus 4 times 1 times 72. Yep, it's an ugly number. All right, so glad I didn't spend too long trying to factor that because it did not factor. By doing what? Split it into what, though? Like we could, but it's none of them will work to give us the same factor in both position. So that's why I don't spend too long, like on these optimization problems, like especially when you get a quadratic here, that usually means the number is going to be ugly. Now, we want to actually calculate both of the x values because they're both going to be positive here. The square root of 112 is, it's less than 11. 11 squared is 121, so 112 is smaller than 11. So 20 plus 11 something, 20 minus 11 something, both of those will be positive. One of these numbers will make sense in the context of the problem, and one of them will be very stupid in the context of the problem. But we won't be able to do that until we have both numbers, like to tell whether they're stupid or not. So 20 plus the square root of 112 is 30.58. And then I divide that by 2. So I have 15.2915, blah, blah, blah. And now 20 minus the square root of 112. This is 9.416 divided by 2. 4.708, blah, blah, blah. All right. So one of those numbers is stupid, but I want you to tell me why it's stupid. All right, so what were you saying?
If the height is 4.7 inches, can't really fit much there.
True, a 4.7-inch box is actually very small. But what were you saying? Yep. So if we actually take the 15.29 and plug it in there, 24 minus 2 times 15, like we're cutting out more than the width of the box. So even though like a 15-inch high box like sounds larger, it would be, except like we basically just have 2 flaps going together. The box wouldn't exist. If we plugged the 15 in, like it'd be positive, negative, positive, like we'd end up with a negative volume. So the 4.7, even though it is not a very big box, it's, you know, It's more like a cookie sheet, just, a cake pan, I guess. But that's the biggest volume we could make. So I will agree, 4.7 is a silly number because it is a very not large box. So they basically cut out a large Post-it from each corner. All right, they had a lot of fun rewriting the description of this particular problem. Imagine you are a wizard attempting to lay siege to an infinitely tall fortress of evil. The fortress is being protected by an intimidating 8-foot wall that stands 20 feet out from the fortress. Luckily, you have crafted a special spell that is perfect for destroying evil fortresses. It can shoot infinitely in a straight line in any direction. However, the more distance the spell travels, the less damage it does. And you only have enough spell slots to cast it one time. How close should you stand to the wall when you fire off your spell to do the most damage? So, this is a question in WebWork that gives students a lot of problems because the description here is very weird. In WebWork, they talk about it as, they say it's a cable. And cables are flexible things. It's not flexible. They should have called it a pipe. So it's probably a translation error somewhere. So this idea of it being a spell that travels in a straight line, this is the context that they're actually meaning in that problem. So we have a picture. So we've got our this is our evil infinite tower. We've got 20 feet away from the base of a tower is an 8-foot wall. So if I stand really close to the wall, like it doesn't have to go very far to get over the wall, but then it's going to have to go really far to finally hit the tower. If I stand too far away, then the distance to get to the wall is going to be too long. So I'm trying to solve for what's this magic distance from the wall. So we end up with this figure here. We know the 20 and the 8. And the variable that we're changing is the distance from the outside 8-foot wall. And what we're trying to minimize is the distance, the length of the hypotenuse of the bigger triangle. So there's a lot of right triangle trigonometry in here, which means we could also use angles as well. So there's a whole lot of different things going on in this ridiculous setup. And there's a reason they went to the effort and just worked the problem. Like, we really hate this problem in WebWork. So in our smaller triangle, I have the length of the smaller triangle, c, x squared plus 8 squared equals c squared. So I have a formula for that smaller distance. Then my larger triangle, so there's two triangles, the small green one and the large blue one. What I do know about the two triangles is they are similar triangles. So I can set up ratios of a pair of sides and another pair of sides. So I need a ratio, I need a formula that uses that D because that's what I want a formula for. That's what I have to solve for. So they wrote D on top, and then they're using the other side that they know. So we've got D matches with C, and then this 20 plus X matches with X. So D is matching with the C formula, 20 plus X is matching with X. So we solve for D and get this horrible mess. Which they went ahead and actually came up with a nicer looking formula, but we are still going to have to use the product rule and then the chain rule inside the product rule to get a derivative of this. It is a extremely disgusting derivative. And to be honest, it's not the way the person who wrote the problem even solved it. Like I dug into the background of the problem, they actually solved it using trigonometry instead. So look, here it is all solved out. Because it's really just not worth the damn effort. So we get our product rule. We end up having to get a common denominator to get everything together. And the top actually simplifies down nicely. It's x cubed minus 1280. And then the bottom is x squared and the square root of x squared plus 64. The bottom, though, only equals 0 when x is 0. But x equaling 0 is actually a maximal distance, not a minimal distance.
How tall is it? Like, it's the same thing as like before, when I asked like, how much does the crop cost? Like, I'm just not understanding like, what we're calculating. Like, how can I think of it?
So in this case, like, they actually described the fortress as being infinitely tall. So it just like goes up however tall it needs to be until the distance is like ridiculous, basically.
Okay.
Because in the problem, like in the context written in WebWork, they don't tell you how tall the building is. It's just tall. So how far do you have to stand away so the distance the spell travels from you to the tower, that straight line, is as small as possible? So we took the setup with similar triangles and set up this ratio, D over 20 plus X equals the formula for C over X. And this, and then we multiplied by 20 plus X, and this was our formula for D down here. And like, cool, that is a formula for D, but I don't want to do calculus on that bullshit. And yet that is what we are stuck with. If I remember correctly, though, this particular question on WebWork, the numbers are 8 and 20. They don't change. Because every time I've worked this problem the last few semesters, even though I wasn't teaching calculus, the numbers were always 8 and 20. Maybe one time it was like 7 and 20. Still, we have all the work. So if we changed the numbers, I could see like, here's where the 8 is. So it's 8 squared, 8 squared. There's my other number, 20. So I've got this 2 spots where they change. I could just track those changes through the math here. So this is something we can take the derivative of. It's just doing the algebra afterwards to set it equal to 0 that it gets messy. So they set up the product rule here. They write their product rule with U and V. So the first part is U. The derivative of U was kind of ugly, so they simplified it. And then the v, the derivative of v, we used our power rule with a negative power. And then they rewrote it, so it's negative 20 over x squared. So let me zoom in a little more. So here are our pieces programmed in from the results up there. All right, so right here, the 20 over x plus 1, they're multiplying the 1 by x over x. And then they turned that into 20 plus x. And then it should have been over x. Oh, but there was an x on top. Okay. So I apologize. They didn't do it that way. They took this x here and distributed through. So x times 20 over x is 20. X times 1 is x. So that's how they got to the 20 plus x on top. And then the bottom was that ugly square root. And then the other side, it's minus 20 times the ugly square root, all divided by x squared. So our red things are getting our common denominator. So our x squared times 20 and times x gives us the 20x squared plus x cubed. And then on this side, we have minus 20 times, we'll end up with x squared plus the square root of x squared plus 64 squared, which cancels the square root. So it's 20 times x squared plus 64, but it's a minus 20. So that minus 20 gets distributed through. That's how we get that other part on top. And so we end up with this crazy fraction as the simplified derivative. When we set it equal to 0 when we solve for critical values of a fraction, we set the top equal to 0 and the bottom equal to 0. I did post these notes online, so you guys can pull this up and see all the work. Like you don't have to worry about copying it down. When we set the top equal to 0, x cubed minus 1280, we add the 1280 and we do the cube root, and we get approximately 10.8577. Now there's a note, there's also a critical point at x equals 0 because that would make the denominator 0. But a distance of 0 is like you're standing right against the 8-foot wall. So that would maximize how far the spell goes, because the spell would have to go infinitely high to attempt to hit the tower. Like it would never hit the tower. So we should stand about 10.85 feet from the wall to minimize the distance our spell will travel. Now, if we wanted to know how far does the spell travel, like if we had every 10 feet the spell travels, it's going to lose, 10 points of damage or something like that, we could make that calculation. I don't know anybody in D&D who does this much math. But that's usually because we don't make people shoot. We don't do 3D in D&D. And then we have the end. So let's look and see what WebWork has for this particular section. I want to see if there were any other like gnarly ones. Oh, I did reopen 4.2, 4.3, and 4.4. Those are due next Tuesday. So is 4.5 and 4.7. So you've got a little more time to catch back up on those sections from last week. Ooh, 10 optimization problems. All right, so let me flip the share just so you guys can kind of see the preview I'm seeing. So this is literally the pig pen problem. But they've labeled L and W for us. So that way down here, when they ask for the length, like, they're asking for the side that goes from the river out, not the side that's parallel to the river. So WebWork is going to often give you the labels for stuff in the diagram, which means they have to draw the picture for you. That also means this is like not very accessible. Oh, this one is asking you to do the problem in two different ways. So they want you to come up with a formula in terms of length and a formula in terms of W. And the formula in terms of length with the way they put the things is actually going to be a little uglier. So I think they swapped the letters from what we did, but it's workable. All right, so this one, a farmer wishes to enclose two identical adjoining rectangular pens against the side of a barn. She wants each pen to have an area of 850 square feet and will use the barn as one side of the enclosure. What's the least amount of fencing needed in feet to create the two pens? All right, so I'm going to draw on the screen what this is supposed to look like. So here's the barn. And then there's two pens. And they want each pen to have an area of 850 square feet. So, like, we can name the dimensions, and then we're doing least amount of fencing. So we need a formula for perimeter, or like a formula for the fencing lengths, because it's not going to be the full perimeter of the diagram. And then we're going to have to use the fact that we know the area of one of the pens is 850 to relate the two dimensions there. So not solving the whole problem, but just if you have problems like visualizing it, just giving you a little leg up on the visualization side. Let's see what the next one is. All right, so they just tell us length plus width plus height has to be less than or equal to 64. And they tell us assuming the height is fixed, find a formula for the maximum value that depends only on the fixed height h. This is bizarre. So they assumed that the length and the width would be equal. I mean, if you're maximizing area with two unknown dimensions, the maximum area for two dimensions is when the dimensions are equal. So if we fix the height as whatever number it is, the leftover divided by 2 is the length and the width, which is where they're getting that 64 minus h over 2 whole thing squared times the h. But this is a poorly written question. I do not like the way this question is written. So I have absolutely no problems showing you guys the answers. Those are literally the answers. Like if they changed the 64, everywhere you see the 64, it would change to whatever number they gave you. So this is trying to get, they called it a curtain rod, but this is like the sofa pivot problem. So you want to carry a curtain rod around a corner joining two hallways. You have to carry the rod this way. One hallway is 7 feet wide, the other hallway is 6 feet wide. What is the length of the longest curtain rod that can be carried around the corner? So I'm going to flip the share back because this is a question that often comes up. All right, so we've got 7 feet here. And 6 feet here. All right, so I do know these are right triangles. And I do know that those two angles there, because these are all right angles, like this creates two right triangles with the same angle, so these are similar triangles. So these other two distances, like the vertical and horizontal distances, I'm going to give those the labels. So I'll call this one X and this one Y. So I can set up a proportion between these two triangles. So I know 7 divided by X, that's the bottom, the horizontal, and the vertical. And then I have to do the same setup, horizontal, vertical, so Y over 6. So if I multiply by 6x, I get 42 equals xy. Now I wanted to maximize the length of that curtain rod, so I need a formula for the length of that curtain rod. And unfortunately, that means we're stuck with Pythagorean theorem or trig functions. Either one will work. It's just whether you want to deal with square roots in your derivative or trig functions in your derivative, and then solving a square root equation or solving a trig equation. Most people tend to go with the Pythagorean theorem here, but the derivative can get a little hairy. All right, so I'm going to call this A and B. So I have A squared equals x squared plus 7 squared. And B squared equals y squared plus 6 squared. So A is the square root of x squared plus 49. B is the square root of y squared plus 36. And our length of the curtain rod is A plus B. Now, before we can take the derivative, we need to substitute in for y or x. I usually will keep it in terms of x because that's what I normally take derivatives of. So that means I need to know what y equals. Which this can be written as 42x to the negative 1. So I have 42x to the negative 1 squared plus the 36, all still under the square root. Now 42 squared ain't pretty, but that's what we get. So 1,764 x to the negative 2 plus 36. So that's what we're supposed to take the derivative of. And we're going to end up with 2 fractions. We then have to get the fractions together. It gets pretty ugly. It is not this ugly on the test, but there is absolutely an optimization problem on the test. All right, let me double check real quick, see if anything else was super crazy. Yeah, so problem 6 is the wizard problem, but it's a wall and then the length of the shortest cable Just remember the cable is really a pipe. We can't bend it. A lifeguard with a circular pool. That is going to be interesting. All right, real quick, let me just throw problem 10 up here. So we have a rectangle inscribed in a right isosceles triangle with a hypotenuse length of 8 units. All right, so there is roughly a right isosceles triangle. So isosceles means the two legs are the same. And my hypotenuse is 8. So this actually means that the two sides are 8 over the square root of 2, which when we rationalize becomes 4 square roots of 2. That's the dimensions for the triangle. The rectangle I'm just putting a point on the hypotenuse, and this point can slide around. So I can have a tall, skinny rectangle, or I can have a really wide, short rectangle, or somewhere in between. I'm trying to maximize the area of the rectangle. So that means I need labels for the dimensions of the rectangle. So I'd go with X and Y. But now I need a formula that relates X and Y together. Hold on. Let's make it X and Y this way. So it's like X is horizontal, Y is vertical. Because I think the way you actually relate it is I'm going to put in the X and the Y axis. I can actually come up with the equation of that hypotenuse in terms of X and Y. And that actually gives me a formula that relate X and Y. So the y-intercept of that line is 0, 4 square root of 2. And then the x-intercept is 4 square root of 2, 0. So our equation actually ends up being a slope of -1x plus 4 square roots of 2. If you find the equation of the line through those 2 points, that's what it ends up being. And now I can plug that in place of y. It's a little annoying, but then I can take the derivative, figure it out.
Also with a 4 term 2 minus 8.
So 4 square root of 2, yeah, you could write it as 4 square root of 2 minus x, yes. I was just writing it in mx plus b form because that's how my brain was deriving the formula. like, it'll end up being a square in there, so, yeah. We are actually a few minutes over, I apologize. Let me hit stop on the recording.